Hello, and we're back and we're talking about calories. Okay, we talked about calorie being the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. Now, this is a fairly small amount of heat. Okay, and so it's a calorie is a small amount. Now, it is heat, so it can also be measured, and heat is energy, so it could also be measured in same units as all energy, and energy is measured in joules, just like work is. And so we can measure this in joules. And in that system, 1 calorie would be equal to 4.18 joules. Okay, and so we said that 1 calorie is a small amount of heat energy. That means that joules, it takes 4 of them and a little bit more to make 1 calorie. So they're even smaller units of energy. And so once again, we talk about work, we tend to talk about kilojoules or something instead of just joules, because joules are a very small amount of work. Now, it turns out that when we use calories for food, we take about the energy in a piece of food and we talk, oh, well, it's in so many calories. Okay, but generally speaking, that is a big C calorie. All right, so we have a big C calorie, all right, or sometimes we just call them food calories because it gets confusing. If it's the first of the sentence or so forth, if it's capitalized or not. And food calories are actually equal to 1,000 calories, or 1 kilocalorie. Okay, and so when we measure, say, a candy bar has 220 calories, those are food calories. It's really 220,000 little c calories. Okay, and so we use food calories, or big C calories. It's actually a kilocalorie, or 1,000 of the smaller measurements, because otherwise you would have 6-digit numbers every time you were trying to figure out how many calories were in any kind of simple little food. Okay, and so it just makes it a lot easier to calculate with. So food calories and the calories that measure heat and water are the same thing. It's just that a food calorie is equal to 1,000. It's a much bigger unit. It's a kilocalorie, all right, of the other kind. All right, now another important characteristic when we're talking about heat is the specific heat of something, or the specific heat capacity is the official word for it. But sometimes we just say it's specific heat for one substance or another. Okay, but technically it's the specific heat capacity of a substance. And what this is the amount of heat energy amount of heat energy, or thermal energy, okay, that it takes to raise the temperature of 1 gram of a substance 1 degree Celsius. All right. Or, since they're the same, it could also be 1 Kelvin. All right. So either 1 Kelvin or 1 degree Celsius. So how much heat energy does it take to raise the temperature of 1 gram of something 1 degree? Now, someone says, oh, that might be about the same. But think about this for a second. Say we have a hot plate illustrated by this excellent square right here. We'll just say this is a little burner thing on top of it. All right. Now, if I put a chunk of metal, or I put a container of water, and we will just say, for the purpose of this discussion, that they have exactly the same surface area touching the hot plate at the bottom. Okay, which one is going to heat up quicker, or are they going to heat up at exactly the same? If you set them on there for 5 minutes, turn the heat up to high, and then you stick your finger in the water and grab the piece of metal, are they going to feel the same temperature? correct answer is no, not at all. The metal will be much hotter. Water, as you know, if you ever tried to boil something, pasta or eggs or whatever, it seems like it takes forever to heat up. Okay, now the same amount of heat energy is going into the metal as is going into the water, and so, but they do not heat up at the same amount. Okay, and so we talk about inertia being an object's resistance to motion or change in motion. Okay, we can think of this as thermal inertia, or think of it as temperature inertia. In other words, it doesn't want to change its temperature very much if it has a high specific heat. Other objects, like the metal, they change their heat really quick. You add a little bit of heat to them, they heat right up. And so they have a low specific heat. Okay, and that's something you have to keep in mind. A low specific heat means it doesn't take much thermal energy to raise the temperature 1 degree. And so these things are going to heat up very quickly. Okay, something with a high specific heat means it takes a lot of thermal energy to make the temperature to go up, just like water. And so it's going to take a lot of thermal energy. Therefore, they're going to heat up slowly. All right. Now, what about cooling down? Well, you're still changing the temperature. Okay, so if it has a lot of inertia, it means it doesn't want to change its temperature. So things with a high specific heat, or thermal inertia, are going to cool down slowly. So water, once it's heated up, will keep its temperature high for a long period of time. Okay, the metal, on the other hand, if I knock it off this heat plate, set it over on the table, it will cool down quicker than the water. So low specific heat means you will heat up quickly. You will also cool off quickly. A high specific heat means you will heat up slowly, but you'll also cool off slowly. Okay, and this is good for us. We are made mostly 3/4 or so of water in our bodies. So if we go outside in the sun, we do not heat up very quickly. The surface skin might heat up if we're getting direct sun on it, but in general, our body would heat up slowly. If we were made of metal, our body would heat up very quickly, and we would quickly overheat. We can only get 104, 105, 106. If we get up to those temperatures for very long, enzymes in our bodies start to denature and be destroyed by the heat, and our bodies quit functioning properly, and eventually we're going to die from it. Okay, so same thing with cooling down. If we were metal and we walked outside on a cold, our temperature would plunge down, but fortunately for us it does not, because we have mostly water and it slows down slowly, and so it takes a lot longer for us to freeze or get frostbite. Okay, and so that is a fortunate thing for us. Also, it's true around the ocean. If you live near an ocean, for example, in Houston, I just got back from Houston, and the temperature did not get as hot there. Why? Because it was near water, and the water absorbed a lot of the energy. It also does not get as cool at night. It stays warmer overnight because during the nighttime hours, the water gives off some of that heat that it has stored up during the day, and that keeps the temperatures about the same. Here in farther inland, up here around Dallas and Fort Worth, it will get hotter during the day because we're surrounded by land mostly, all right, and then it will get cooler at night. It's not as cool as we'd like, perhaps, being in the middle of summer, but it will get hotter in the daytime, cooler at night than it would on the coast, where the water, since it doesn't heat up as fast during the day and it doesn't cool down as much at night, it keeps the temperature more moderate. The next concept we're going to talk about is thermal expansion, the idea that when things get hotter, they tend to expand. When they contract, they cool down. Now, we can think about that as in terms of gases, for example. If they heat up, they can expand a great deal. This is why hot air balloons heat up the gas in there. They spread out. As they heat up, they expand and spread out, and therefore they become less dense. So that allows the hot air balloon to rise. Okay. Gases expand the most when they are heated, and they contract the most when they are cool down. Liquids would be the next most likely. They would rise more when they're hotter, and they would contract. If you were just watching a pan of water as it heated up, though, you would probably not notice that it really expanded a lot or contracted when it got cold. Solids expand and contract the least, but once again, they, as a general rule, will expand when they get hotter, and they will contract when they get colder. One exception to that is water, and water still applies to that until you get to a certain temperature, but we'll talk about that in a minute. Okay, so the biggest thermal expansion and contraction, depending on heat and cooling, are gases, followed by liquids, and then the least would be by solids. All right. However, just because it's least doesn't mean that's not important. Okay. For example, and we'll do some examples like this hopefully next when we do our lab stuff and look at our lab day. We'll see some of these things. But basically, they're what they're called bimetallic strips. Bi because there are two metals, one on one side, like this one's brass on one side, iron on the other side. If they're at room temperature, they expand about the same amount, and so it makes a nice flat piece of metal. However, if you get colder, the brass contracts more, and since it gets shorter, basically, it causes the metal to bend up. On the other hand, if you heat it up, the brass expands faster because it has a lower specific heat, and so it expands faster, which causes it to bend. The only way it can get longer and still be attached to the iron is to bend, because the outside of the curve is going to be longer than the inside of the curve. And so a change in temperature will make this bimetallic strip, which you have two metals that have different specific heats. One will bend when it gets colder, will contract more, and when it gets hotter, will expand more, and so it will cause this piece of metal to move. That concept has been most often put to use in thermostats. Now, some thermostats are different now. This is an older type, which used to be called a mercury thermostat. You have this little drop of mercury. Mercury is a metal, conducts electricity. And when it's over here, these two wires, which would run to your furnace or air conditioner, as the case may be, there would be no way for the electricity to go here, and so your furnace or air conditioner would not run. Okay? As it got colder, this bimetallic strip would begin to coil up tighter, which means it would move this direction. That would make the mercury, a little ball of mercury, as this gets over the top, it would roll over here, and now your roll would be touching those two wires, and it would turn on your furnace. Okay, if you had different ones over here, you could have it or do an air conditioner, and then it would go back and forth, and it would keep your temperature. So once this furnace, if this were the furnace, it would heat up. That would make this coil back the other direction. The mercury would fall to the other side, and it would break your connection. Your furnace would turn off. If it began to get cold again, then it would contract and pull this direction, and the mercury would touch the wires, and it would turn your furnace back on. Okay, and like I said, most of the time now we have central air and heating, so you would have this where depending on which side of this it touched, it would cause it to click on. Now, mercury is not used very often anymore because mercury switches are considered dangerous. I have some mercury switches we'll look at, and they came from an old school that I was in the thermostats that were on the wall. All right, but that's another example. Now, other examples of thermal expansion. If you build a road, well, a road is insulated because it touches the ground, and the ground stays about the same temperature. But if you have an overpass, air gets underneath it, and that's why you always hear people say, watch out for icing in cold weather and rain on overpasses. Why? Because underneath the road gets the same air temperature as above it, and so it cools off much quicker than a road that's going on top of dirt. Okay? Now, because of the change in heat and stuff, if the road starts expanding and contracting based on getting hotter and colder, then it would start crumpling. Okay, this still happens on roads sometimes, and we end up, as it crumples and goes back and forth, expands and contracts in the summer and the wintertime, it'll break loose some of the asphalt and you have potholes. All right, but this is especially critical on an overpass because it really has bigger temperature changes. So if you'll look on most overpasses, you will see a little zipper, metal zipper looking thing here, and this gives room for it to expand and to contract without buckling the road. Okay, and so you will see this little metal zipper going across it. Okay, also sometimes they will have little rocker things here that will allow it to rock or move a metal bridge or something to move back and forth and expand and contract. It gives it a little bit of room to wiggle, so to speak. All right, now sometimes it can be drastic. If you were to see this picture up here, you would probably assume that, oh, this is some kind of hurricane, earthquake or something that's come through here. But basically, these are railroad tracks that just due to extreme heating had expanded, and they expanded to such a point that they changed their shape, and obviously it's not a good place to send a train now. They're going to have to replace that track before they can actually run a train back over there. So thermal expansion can be a very serious problem. Now, like I said, also using oven thermostats that tell us to kick on and off, refrigerators, the same thing, and even toasters. And we'll come back next time for our next topic, under heat.